Hello, welcome to the brand new section of the course, The Broker, Apache Kafka. The aim of this section is to familiarize the reader with Apache Kafka and show you how to solve the consumption of millions of messages in pipeline architecture. Here we show some scalar examples to give you a foundation for the different types of implementation and integration for Kafka producers and consumers. In addition to the explanation of the Apache Kafka architecture and principles, we'll explore the Kafka integration with the rest of the SMAC stack, specifically with Spark. At the end of the section, we will learn how to administrate Apache Kafka. Let's get started with the first video of the section, Introducing Kafka. In this video, we will look at the features of Apache Kafka and use cases. So basically, there is not much of a relationship. Apache Kafka is mainly optimized for writing. Nowadays, real-time information is continuously generated. This data needs easy ways to be delivered to multiple receivers. Most of the time, generators and consumers of information are inaccessible to each other, and here is where integration tools are required. In the 80s, 90s, and 2000s, the large software vendors, IBM, SAP, BEA, Oracle, Microsoft, Google, and so on, found a very lucrative market in the integration layer. Here we can find enterprise service buses, SOA architectures, integrators, and other panaceas that cost several millions of dollars. In the era of fast data, the first challenge is data collection, and the second is to analyze this huge amount of data. Now let's look at the features of Apache Kafka. Message publishing is the mechanism for connecting heterogeneous applications by sending messages between them. The message router is known as a message broker. Apache Kafka is a software solution to deal with real-time information and route it to consumers in a quick way. The objective of the message broker is to provide seamless integration, but it has two collateral directives. The first is not to block the producers, and the second is to isolate producers and consumers, so as not to let the producers know who the final consumers are. Apache Kafka is a real-time publish-subscribe solution and a messaging system. It's open source, distributed, partitioned, replicated, commit log-based, and a publish-subscribe schema. Moreover, its main characteristics are: it is distributed. The cluster-centric design supports the distribution of the messages over the cluster members, maintaining the semantics, i.e., we can grow the cluster horizontally without affecting the consumers. It has a high throughput. As we mentioned, all the technologies in the SMAC stack are designed to work on commodity hardware. Kafka can handle hundreds of read and write operations per second from a large number of clients. It has multiple clients. Easy integration with different clients from different platforms: JVM, Clojure, Java, Groovy, Scala, Ceylon, Python, .NET, PHP, Ruby, and so on. It is persistent. It doesn't allow any data to be lost. Kafka is designed with efficiency, so data structures provide constant time performance access no matter the data size. It is real-time. The messages produced are immediately seen by consumer threads. These are the basis of the systems called Complex Event Processing, CEP. On the producer side, we find several types of actors. For example, there are adapters, generating data transformations. For example, a database listener or a file system listener. There are logs, for example, the log files of application servers and other legacy systems. Proxy, generating web analytics information, for example. Web page, front-end applications generating data. Web services, this is the service layer with invocation traces. We could group the clients into three types. Offline clients. The information is stored for a deferred analysis, for example, Hadoop or data warehouses. Near real-time. The information is stored but could be requested at the same time, for example, NoSQL databases like Apache Cassandra. Real-time. The information is analyzed as it is generated. We need a modern engine like Apache Spark or Apache Storm to make an analysis over HDFS. As we've mentioned, fast data is the new ingredient of internet-based systems. Simply to operate a web page, we need to know user activity, logins, page visits, clicks, scrolls, comments, heat zone analysis, shares, and so on. Traditionally, the data was handled and stored with traditional aggregation solutions. Due to the high throughput, the analysis could not be done in the same moment. Today, yesterday's information is generally less valuable. Offline analysis like Hadoop is being left out of the game. There are several examples of Apache Kafka use cases. First is application security, login analysis, brute force attack detection, systematic denial of service attack detection. Second is collecting the data from device sensor, including sophisticated sensors like surveillance cameras to GPS cell phone sensors, and traditional sensors like light, temperature, pressure, and humidity. There are others such as collecting logs from business systems like application server logs, ERP, CRM, and so on, focused marketing in real time to huge public spaces, recommendations based on correlation, popularity, and so on. Sentiment analysis, market tendencies, consumer segmentation, web search, based on relevance. In all these cases, the analysis is done only in real time. It's now or never. Apache Kafka is usually compared with traditional messaging systems such as ActiveMQ or RabbitMQ. The difference is the data volume that Apache Kafka can handle in real time. Kafka is a message broker. This means that the message delivery between 2 points is guaranteed. An ESB consists of multiple components where a message broker is usually one of them. Besides that, ESBs serve more purposes than just message transport. The ESB also deals with protocol transformations. An ESB also monitors, controls, and routes message exchanges between services, solves connections between communication service components, controls service deployments and versioning, marshals the use of redundant services. Let's look at use cases. We have already seen which business scenarios are solved with Apache Kafka. However, this is an architecture book, so in which layer in the architecture should we put Kafka? Here are some real use cases. Commit logs. If a system is without a log system, then we can use Kafka. Often a system does not have logs simply because in the past it was not possible to handle huge data volumes effectively. There are a lot of horror stories about application servers failing because they could not write their logs correctly, with the verbosity needed by the business. Kafka can also help to start and restart fallen log servers. Log aggregation. Contrary to what one might think, much of the work of the on-site support team is log analysis. Kafka not only provides a system for log management, but can also make heterogeneous aggregation of several logs. Kafka is a replacement for traditional log aggregation solutions. Log aggregation typically collects physical log files and puts them in a central place, a file server or HDFS, for processing. Kafka can physically collect the logs, removing the implementation details such as the file location or format. In addition, its process has low latency and supports multiple data sources when making distributed consumption. Messaging, the most popular use for Kafka. Systems are often heterogeneous, and instead of rewriting them, we have to translate between them. Often the manufacturer's adapters are unaffordable, and for such cases, Kafka is the solution, as it's open source and can handle more volume than many traditional commercial brokers. Record user activity. Many marketing and advertising companies are interested in recording all the customer activity on a web page. This sounds ambitious, and until recently it was very difficult to keep track of every click that each user made on a site. For those tasks where data volume is huge, we can use Kafka for real-time processing and monitoring. Stream processing. We could write a whole book about this new topic. In some business cases, the process of collecting information consists of several stages. A clear example is when a broker is used not only to gather information, but to transform it. This is the real meaning and success of the Enterprise Service Bus (ESB) megaprojects. With Kafka, the information can be collected and further enriched. This, very well paid today, enrichment process is known as stream processing. All this seems good, but who is using Kafka today? Here are some examples. LinkedIn, used for activity stream and operational metrics. Can you imagine today's LinkedIn newsfeed without Kafka? Here's more information. Twitter, The Twitter whale is a new unicorn. Handling 5 billion sessions a day in real time requires Kafka as their stream processing infrastructure. Netflix. Thousands of hours watched per minute, and Kafka is the backbone of Netflix's data pipeline for real-time monitoring and event processing. Spotify. Thousands of hours of music per minute, and Kafka is used as part of their log delivery system. Yahoo. Used by the media analytics team for the real-time analytics pipeline. Their cluster handles 20 gigabytes per second of compressed data. In this video, we have learned the basics of Kafka. Awesome!